Yes, recording on. Okay. Uh, I am again thankful to Dr. Tabish Alam sir for accepting our invitation to deliver a talk in this 6 days ATAL sponsored faculty development program. It is my proud privilege to introduce Dr. Alam sir. Dr. Tabish Alam is a senior scientist at Council of Scientific and Industrial Research, Central Building Research Institute, Roorkee, with expertise in heat transfer enhancement, solar thermal systems, computational fluid dynamics, and building physics. He earned his PhD and MTech in thermal engineering from Indian Institute of Technology, Roorkee, and BTech in mechanical engineering from Aligarh Muslim University. Dr. Alam has held prestigious postdoctoral positions at Indian Institute of Technology, Bombay, and Kyungpook National University, South Korea. Recognized for his outstanding contributions to research, he was listed among the top 2% scientists globally by Stanford University in 2024. Dr. Alam has made significant strides in sustainable energy and thermal engineering, earning such as the Diamond Jubilee Best Technology Award for his innovative HVAC ducting system integrated with COVID-19 disinfection solutions. He is also a recipient of Santi Soma Sanyal Memorial Award for the best paper published in the Journal of the Institution of Engineers, Series A, Springer publication. He is an active member of Bureau of Indian Standard Committee, CHD 27, on thermal insulation material, contributing to the development of national standards. Dr. Alam is a member of the editorial board of Scientific Reports by Nature Publishing Group and serves as associate editor in Thermal Science and Engineering and Energy Systems, Energy Efficiency in Building and Urban Environments, and the Journal of Engineering. With an extensive publication record in high impact journals, Dr. Alam continues to advance energy efficiency and thermal systems through his research, editorial roles, and active involvement in standardization efforts. I again welcome you, sir, in the 6 days online AICT sponsored faculty development program on clean energy and environment sustainability. Thank you, sir. Over to you.
Okay, thank you, Abhishek ji, for introducing. So I can share my slides.
Yes, sir. Murli, Dr. Murli, sir is co-host.
Yes, sir. Yes, sir.
Yes, sir. You can share, sir.
So it is visible?
Not now, sir. Yes, sir.
It is visible?
Yes, sir. It is about to open.
Yes.
Yes.
So today's topic is very important topic.
Sir, can you make full screen?
Wait.
Slides.
Full screen share kar.
Yes, sir.
It is visible?
Yes, sir. Just open.
This topic is the very important topic, that is we have see the COVID-19 pandemic. Everybody have seen COVID-19 pandemic. So there is a lot of life has been lost, and we have the very emergency phase in our life. So I think this is the one of the worst phase in the century. So good evening, everyone. Good evening, everyone. So today I will discuss the critical issues of the indoor air quality and its role in the transmission of the airborne pathogens, particularly in the light of the COVID-19 pandemic. So we will explore the advancement in air purification technologies and their potential to improve the indoor health and safety. Basically, this pandemic is started. WHO declared this SARS-CoV-2 a public health emergency on January 13, and after that, it is declared as a pandemic on March 11. It did, initially, it was thought that this virus is spread uh, through the respiratory droplet which settled on the surface due to the gravity. However, there is this at the initial stage there is a some study comes that prove that this virus is airborne and transmitting over distance of several meters, particularly in the closed indoor environment such as the residential, office, commercial building, school, hostel, or hospital. These the poor indoor air quality has been linked to increase the transmission rate of the viral infection and associated with the mortality and morbidity from the cardiovascular, respiratory, and other diseases. So actually, with the light of these pandemic, we have work on the air handling unit because in the central air conditioner we have to we have to circulate the air in the indoor. So these are the major thing that can separate the virus in the entire building. So, in the light of this, the several guidelines is being released by the different agency for operation of the HVAC system. We will discuss this and what internationally there is a number of the guidelines available which comes in the light of the this pandemic, and in the national guidelines has been released for the operation of the HVAC. So with this the CSIR is also released their guidelines for natural ventilation building and the force ventilation building. So, with the help of these guidelines and these studies, we develop a test bed facility to test the different scenario in the air handling unit, how we can integrate the UVC light to reduce the impact of the coronavirus into the indoor environment. When we carried out a lot of simulation to simulate the air circulation spreading of the virus into the building, and we also develop a standalone air disinfectant system that can be used for the in the closed rooms. So these actually the number of pollutants like SOx, NOx, PM10, M2.5 that can be very harmful for a in the view of the health. These pollutants are also facilitate the growth of the transmission of the airborne pathogens, including the mold, bacteria, fungi, virus. In the initially WHO ASHRAE REHVA guidelines recommended increasing the ventilation or using room disinfectant systems such as this standalone air disinfectant system we have developed with the UVC when integrated with the UVC to combat the indoor virus transmission. There is a HEPA filter, there is a UVC light, there is a coating of the antivirus coating that prevent to reduce the virus to kill the virus in the air. So basically, here, what is the air handling unit? Air handling unit is the assembly of the air conditioning component that we can see in the central air conditioning. We have the air handling unit that can force air to uh, cold air to force into the space which has to be conditioning. There is a number of components like fans, cooling coils, filters, humidifier, damper that is integrated into self-contained package and installed as a single unit which connected to the system of the metal duct and distributed to the conditioning air. So there is a supply duct which has to provide the air into the room which has to be conditioned, and there is a return duct which can return back to the AHU system. So there is a recirculation is there to save the energy. So these are the conventional air handling unit in which can we can see the air is recirculating. So if there is a one person, one infected person is there, so it can separate the virus in the entire building due to the recirculation of the air. So this is the one of the air handling, conventional air handling. So we have done the lot of modification in the this, and we have integrated the UVC light to reduce the impact of the coronavirus into the human being. So, what is the purpose of air handling unit? Air handling unit condition and distribute the air within the building. That we have to dehumidify the air, we have to cool the air, and we have to supply it into the building. It also takes the fresh ambient air from the outside, clean it, heat, and cool it, and it's maybe humidified when those region there is a low humidity is there. So most of the units will have a additional duct run to then pull to use dirty air out of the room back to the AHU. So the purpose of this fresh to take the fresh air to reduce the impact of the virus. Some of the return uh, air might be recirculated back into the fresh supply to save the energy. So generally, 30% of fresh air we can take with the circulation air. So as as per the standard, so 30% can be used. So in the trains we can take 30%, but in the coronavirus in the coronavirus pandemic, so some guidelines suggested that we have to take 100% fresh air. That although can take the 100% fresh air, but this 100% fresh air can increase the energy consumption into the building. So air handling unit is used to recondition and recirculate air as a part of the HVAC system. So actually, a 100% recirculation because in the yesterday presentation we have seen the HVAC is the bigger consumer, energy consumer into the building that can consume 40% of the energy of the building. So if we run the AHU, air conditioned AHU on the 100% fresh air, so very high amount of the energy will be consumed. So there is a some technologies available that can be used in the air handling AHU or air conditioning, so which can reduce the impact of the viruses. Building where the hygiene requirement for the fresh air are lower, some of the air from the rooms can be recirculated by mixing chamber, and this can result in significant energy saving. But the HU connected to the duct work that distribute the conditioned air through the building and return it to the AHU. So we in this scenario when we can use the 100% fresh air, so we in this condition we can use the heat recovery, heating cooling recovery, heat recovery exchanger that can exchange the heat between the incoming and the fresh air, and fresh air to reduce energy consumption, and simultaneously we can utilize the 100% fresh air. So in order to operate the HVAC system in the corona pandemic, there is in order to reduce the SARS-CoV-2, uh, how we can run the HVAC system till June 2020. HVAC related institution like H-Ray, Raheva, SASE, and Architecture Society of Chinese session of the refrigeration. They have proposed the how we can use the HVAC system to reduce the impact of the SARS-CoV in the indoor air, in the indoor spaces. So these are the guidelines that suggest how we can operate the how we can approach the air conditioner. So we can say this ASHRAE, they suggested increase, we can increase the amount of the outdoor air, and they suggested to use 100% fresh air if possible. So Similarly, the Rehva, they can suggest it to 100% fresh air and open window regularly. So we can exchange the air from the outside. So Sase also suggested to use the 100% fresh air and open windows regularly. So there is a other uh, guideline provided by the China that the 40% ratio of the outdoor air should be greater than the 40%. So this is related to the outdoor air operation of the HVAC. So operate HVAC related to the device local keep and system on for the 24th a day. So that is very important. So similarly, there is every international agency has provided the this guideline for the operation of the HVAC. So, and how can we maintain the temperature and humidity set point? They also suggested control the temperature and humidity is beneficial, but the temperature and relative humidity set point should be considered on the case by case basis. That is depend on the spaces, which spaces, like for the hospital we have to use the different set different temperature humidity set point, and for the office building there should be another temperature of the humidity set point. So there is no need to, as per the REVA, there is no need to adjust the temperature and humidity set point. And as per the SASE, there is a temperature should be controlled between 70 to 28 degree, and the relative humidity should be controlled between to 40 to 70%. And this Chinese society does not mention any related to temperature and the set point. So these are the basic comparison we have done, how we can use how these societies recommending the air circulation into the building by using the HVAC system. The most important is the air cleaning. So ASHRAE is recommended the HEPA filter in the HEPA filter and UVGI ultraviolet radiation. They are recommended to disinfectant the this ducting system air, and this REHVA also recommended to locate the air cleaning device close to the breathing zone, like in the damper where we have to supply the air into the this spaces, and a special UV cleaning equipment should be there to disinfect to disinfectant the surfaces in the ducted. So SASE also propose this type of the air cleaning and ventilation is more effective than the clean air. So UV is also recommended by the Chinese society. So, in the light of this, ISHRE guidelines is also published in India, Indian Society of Heating, Refrigeration, and Air Conditioning. They also published the, the recommendation to operate the HVAC. CPWD is also recommended as we are working in Council of Scientific and Industrial Research. So we work on the guidelines and we publish our guidelines, CSI guidelines for ventilation of residential and office building. There is a two version is there. In the initial stage we have published first this guidelines. Later on, after 1 year, we have published the second version of the guidelines on the ventilation of residential and office building. And these guidelines are available on the CSIR website, so everyone can download freely and can be uh, utilize the recommendation which has been provided by us. So ISHRE guidelines uh, uh, basically uh, that is related to the humidity, temperature, how we can control the virus and how we maintain that humidity. So low humidity increase the infectivity of the bacteria. 40% RH is considered the threshold. So relative humidity should not be less than the 40%, and the 80% and above RH tend to neutralize the COVID-19 virus, but this will increase the dust, mist, and fungi. Basically, the high humidity is, that combat to the coronavirus, but at the high density, there is a water vapor in the air is there, so it will increase the dust, fungi, which result in the respiratory diseases like asthma. And also, this ISRE guideline recommended the temperature range should be in between the 24 to 30 degree, and also we recommended the 25 degree. So high temperature and high humidity significantly reduce the temperature transmission of this viruses. So SARS-CoV has been found highly stable on the surface for 40 days at 4 degree, 1 day at 37 degree, and 30 minutes at 50 degree temperature with need to be inactive virus. So in this way, you can see that higher temperature is beneficial to reduce the virus impact. But the comfortable human temperature is between it is around 23 degrees, so we cannot so this on the basis of this, the comfortable temperature has been recommended for particularly in the virus pandemic is 24 to 30 degree. So these are the guidelines for the residential. So these are the some guidelines that has been recommended, that AC reduce the humidity and control temperature. That is the option, and circulation of the fresh air by tightly open door, window, and exhaust. So we have to circulate. We have to take the fresh air. Fan filter could be used by preventing PM10, PM2.5 into. So there should be a HEPA filter which can reduce the PM10, PM2.5. Kitchen and toilet exhaust fan kept operational. Rooms at temperature should be between 24 to 30 degree, and relative humidity is between 40 to 30 degree. In the humid climate conditions, set temperature near to the 24 degree, or in the dry climate, the temperature near should be the 30 degree. And use of in additional to this temperature set, we can use the fan for dilute the concentration of the viruses in the indoor air. So these are the some recommendations that have been provided by the ISRO guidelines. So they also provide the guidelines for the commercial building, that is based on the categorized based on the type of the indoor unit installed, like multiple cassette units, multiple high wall units, or tower unit, ducted units, fan coil unit, and air handling unit. So set temperature in between they have recommended the same temperature range and same relative humidity, that is between 24 to 30 degree, and humidity between 40 to 70 degree. The in humid climate, they recommended the set temperature 24 degree, and in the dry climate they recommended to the 30 degree with the use of the fan. So as they have recommended to use the 100% fresh air in the air condition. So they are also recommended the heat recovery will that could be used, that could be used to reduce energy consumption, and kitchen and toilet exhaust fan must be kept operational every time, and advisable to introduce a fresh air duct attached to the central inline fan filtration unit. Fresh air must be ensured 100% minimum fresh air of 3 cubic meter per hour. So these are the recommendations that have been provided, that have been suggested by the state. So CPWD guidelines, they also suggested the AC temperature is to be set between 24 to 30 degree and relative humidity 40 to 70%. And there should be a maximum possible fresh air that could be from the window, that could be from the fresh air duct air. There should be use air sanitization like filtration of the indoor unit, the available device equipment. There should be there is a window doors opening can be used for fresh air intake. Ceiling fans can be should be in the running condition, so it circulate the air in the entire room, so it can dilute the intensity of the virus in the room. So evaporated type air cooler, ducted cooling plant uh, can be has been recommended. So these are the some basic, these are the number of the guidelines that has been given by the CPWD control environment, uh, moderates the risk of the exposure and concentration, maximum exposure and concentration. So in different scenario, they have provided the room temperature and humidity, set humidity for the different scenario, like when we are using the window AC, split AC uh, rooms aided with the maximum fresh air intake. And this also recommended the air changes per hour in the room. There it should be more than 12 ACTH, and there should be a exhaust fan for the to create the negative pressure. So in the light of, in the light of this, in the light of this, we have developed the net facility to test the different scenario or where we can integrate the UVC light into the ducting system. So basically test bed facility for determining the functional and operational parameter of the COVID-19 disinfectant solution. This can evaluate the different operational parameters such as the airflow rate, air velocity, temperature, humidity, and we can determine the dust cleaning frequency, cleaning time of the UVC lab module, and we apart from the UVC disinfectant system, we have the another disinfectant system, that is aerosol based oil droplet deposition, that can be this aerosol. We can supply aerosol in the air to with the air into the room, so it can reduce the impact of the virus. So mounting and we have developed the mounting technique and retrofit technique of the UVC light into the existing system, and the application of the developed system in one of the selected buildings. So using this technology, we have retrofit many offices. Even though we have retrofit into the Parliament House, the HVAC ducting of the Parliament House. So these are the HVACs, HV layout of the HVAC system. In this HVAC system, uh, uh, we have the this air handling unit. So we have number of component is there. So we have the fresh air intake duct, and there is a recirculating duct. This is the recirculating duct, and this is the fresh air. So we have the mixing chamber, we have the HEPA filter, we have the cooling coil, we have the heating coil, we have the blower, we have the filter, then we have the humidifier. So we can control the humidity of the air, temperature of the air, and we have a number of the terminal box to measure the different parameter, and we have retrofit the UVC light into the duct. So we have measured different parameter, uh, uh, and we have created the turbulence into the air to study the impact of to study the different performance of in the duct. So this is the layout. So actually we have uh, three room. One is the HU room. This one, this is one. We have the hall. This is the big hall, and this is the small room like office space. So we have designed this HVAC system into the in such a way that we can conditioning this space, and we can conditioning this spaces alone, and we can conditioning this office room alone, and we conditioning the both the office room and the hall simultaneously, and this is in the separate room. So there is a number of sensor UVC boxes there. This ducting is the modular type, so we can remove the part of the duct, and we can integrate any UVC light, any sensor easily. So basically, these are the ducting system. So this is the HU. This is the photo of the hall, and this there is a one room is there. This is the HU room. So there is a terminal box is there. You can see. So there is a number of the sensor is installed to measure their humidity, temperature, PM, virus, the PM 2.5, PM 10. So we can control the various parameters. So we can control air velocity 10 to 0 to 10 meter per second by using the centrifugal blower controlled by BFD, airflow volume 0 to 2200 CFM, cooling side temperature that we can go up to temperature of 16 degree that using the chiller unit. We can go the heating side temperature, then we can go from ambient to 50-degree temperature. We can control the humidity from ambient humidity to 90%. Humidity, the mixing ratio of the fresh air with the circulating air 0 to 90%, and the duct design that has a modular structure. So we have we can study using this ducting system into the three case. The uh, this is the case one. So in the first case, there is a big hall is there. In the second case, there is a one room is there. In the third, second case, the one room is there. In the third case, we can conditioning both. So you can see in the sorry, in the first case, the HU is running into the circulation like this. So no air is going outside. So entire ducting is in the recirculation, and in this case too, we conditioning the this hall. So you can see we are releasing the air here, and we are intake duct air. So we releasing the air, and it's circulating in the space, and taking back into the air duct. In this we are conditioning the room only. So in this way, we are releasing the air into the room, and it's circulating in the room, and this we are taking this air into the uh, return duct. So this is the first case. So you can see the air is circulating into the duct only. And this is the second case where we are conditioning the big hall like auditorium hall, cinema hall. So we have simulated like this, and this is the uh, this is the simulation of the room. So in this way, we can conditioning the office room. So using this facility, we can test the performance in three different ways. So these are three type of the case is there: closed duct loop, closed duct loop for the disinfection of the circulated air. It is suitable for testing purpose only. UVC light, foggy, essential oil type of the solution for coronavirus. There is a no load, no thermal load is there. In the open in the open duct loop, large hall open duct loop for the disinfection of the hall air, suitable for the study of the large space like malls, auditorium, conference room. There is a thermal load of approximately 5 TR. For the open loop, small room, open loop, that for the small room, open loop for the disinfection of the small office room air, that is suitable for the study of the office room air, which have the thermal load 1 TR to 2 TR. That is where we can use the conventional domestic ACs like window ACs or split ACs. So these are the team. This are is the CSIO team which integrated the UVC walks into the duct. So we have this cutting portion we can see here. So we can pull out, and there is a UVC light is there. So we can place into the duct any existing duct. So we have placed this box here. You can see. So this is the location in this diagram. We have shown the UVC box, and this is the which is chose for the room. So you can see there in the room there is a supply duct is there. There is a inlet return duct is there. So this is for the room only, and this is for the big hall is there. So this is the supply duct and this is the return duct in the hall. So also we control the humidity. There is a humidification system we have installed to control to increase the humidity in the room. So we have this day fire is there, and we have the pump. With the help of the pump we can force to inject the water into the this HVAC system, that it can increase the humidity up to the 90% in the hall or either in room. So you can see there is a number of water nozzle is there. So this is for the humidification in the duct. So these are the basically how we can how which amount of the water is has to be supplied in the humidifier, so it can give the desirable humidity. So this is the basic calculation. So using this calculation, we can calculate how much water has to provided for the hall or for the room. So it can we can achieve the humidity up to 95% in the hall, either a hall in the room. So for the this calculation is different for the hall and different for the rooms. So for this purpose, we also carried out the CFD result for the hall. So we can see there is a supply duct is there, and there is a return duct is there. So in this study, we have find out the behavior of the air circulation in the hall, how we can achieving the air temperature distribution in the entire hall. So there is a temperature distribution, and this this line, there is a high temperature. There is this shows that there is a window wall is there. So there is a solar gain is there. That is why it shows the highest temperature. Although there are almost every part of the this hall, the temperature is uniform except this. So this temperature temperature at this wall we cannot control due to there is a some glazing is here. So we have carried out different simulation for different scenario, and we have carried out the simulation using the auxiliary duct system into the room, into the hall. This system was proposed for hospital where the continuous operation of the HU is necessary, and this system allows for the maintenance of the one duct, because in the hospital there is 124 hours HVAC is running in there. So we have give the provision for auxiliary duct when we have the UVC light in this duct. So when suppose the one light is got damaged or is not working, so we can utilize the auxiliary duct. So in that time we can this repair this UVC light, and we can use further. So in this we have triple ducting system. This system allows for maintenance of the one duct while the other duct is in operation. Another duct is provided for operational of the normal duct, which need to be required for the this hospital, like hospital where we have to need the 24-hour HVAC system. So basically, question comes into our mind that UVC light that can disinfect the coronavirus. But how much dosage we have to provide? How what should be the intensity of the light? What should be the residence of the light? So we have done the thorough study in which we have come out that the required dosage should be 1 millijoule per centimeter square should be required to kill the coronavirus. So basically, the required dosage can be calculated using the UVC light, multiplication of the UVC light, and the residence time. So basically, these two parameters provide the UVC dosage. What is the UVC dosage required for kill the virus? So UVC intensity that's depend on the number of parameter, that number of the lamp, light of the exposure, and lamp of the wattage, and the residence time that depends on the air velocity in the duct, airflow rate, the duct cross sectional area. So basically, uh, our aim is to provide the large residence time and a low UVC intensity, because high UVC intensity that promote to the heating into the air. So we work on the and reduce increase the residence time of the air, so we can expose more and more time air to the UVC lights. So this residence time can be controlled by the airflow, by the this volume flow rate of the air, that can be controlled by the BFD fan using the variable frequency drive into the duct and control both flow rate and the velocity. So by using the low flow rate, so we can increase the residence time of the air to expose the UVC light. So the other study we have done, time required for the dust settlement for UV light under continuous operation, operation time of the UV lamp hour, and typically time required for UV cleaning, UV light, UV lamp cleaning, and filtration cleaning. So it do not affect the indoor environment of the buildings. So the we done the some simulation on the UV light in the ducting system is there. So we have a chamber of 2 feet by 2 feet by 2 feet where we have placed the UV light, and the source pattern assumed as a Lambertian sources. So the and we have taken the wall of the chamber which has reflectivity 80%. So so this is the Philips UV 8-watt lamp is there. So we are not changing the intensity of the light, but we are adjusting the ducting or airflow in such a way that we can exact get the dosage of the u by using this lamp into the to expose the air. So this is a basic concept because uh, so there is a number of UVC light available in the market. So from 9 watt, 1.5 watt, 2.1 watt, 2.2 watt. There is a number of the UVC hour, and this is the wattage of the lamp: 4 watt, 6 watt. So we have choose 8 watt UV lamp that has the sufficient UVC light intensity to expose the air into the duct. Uh, what condition is that we should have the sufficient residence time to expose air using this lamp into the ducting system. So these are the conditions. The UVC light will fall on the surface of the wall with reflect multiple times and will uniformly spread out in all the directions. The UVC light is considered as a Lambert short. Why considering this condition, we have calculated the UVC dosage. What is the UVC dosage required for flowing air for a particular CFM in the HU duct? So also this we have carried out the simulation. We have carried out the UVC light intensity of the UVC light at the different planes. So this is the UVC chamber. UVC chamber is the middle plane. This is the side plane on which the UVC light is placed. This is the top plane. This is the front plane. This is the source plane. So we have simulated the source light, and we got the this maximum average value on total flux on the wall. So these are the this data is very helpful to designing the residence time of the air in the ducting system. So when we have used the two lamp into the UVC chamber, so the simulation is also carried out. What should be the maximum values of the UVC light intensity, average value, total flux? So this is for the middle plane, side plane, top plane, front plane, source plane. So this will be helpful to calculate the residence time for when we are using the tool. So in similar way, in we carried out the simulation for the three lamp, five lamp, and we get the residence time for the year. So in order to get this residence time, we also we have carried out some simulation on the air mixing around the UVC. So you can see that when air is found to there is some portion of the in the duct there is a no exposed to the no exposed to the UV light. We can say backside of the this lamp. So we have the recirculation of the air in the duct. So we can in this way we can increasing the residence time of the air, and we are mixing the air the structure in the duct. This twisted tape is very helpful that can provide oxygen inside the pipe. This twisted tape generally fuel or secondary flow, increasing the flow velocity to the tube positioning a blockage and providing an effective longer helical flow path that can increase the residence time for the air in UVC in exposure of the UVC light. So you can see it can increase the retention time. There is no blind spot. Airflow is contact with the UV completely. So 100% air we can ensure using this well motion that 100% air can be exposed to the UV light. So also there is a different type of the duct is there. So we have uh, carried out the simulation of the duct. So this is one of the shape of the duct, volumetric stadium shape. The advantage of this is shape is that it is a multiple reflection on the UVC light. So if we can place the UV light in this, so there is a multiple reflection is there, so it automatically increase the light intensity. So we also simulate the airflow in this shape. So and we calculate the residence time. So there is a streamline shows how we can get the flow pattern in such type of the this ducting system. And we also carried out the for the circular we use this spiral air diverter is there, so it create the spiral motion into the duct that can increase the retention time into the ducting system. So we have simulated the duct of 1.5 feet. We have work on the different. We have taken the different pitch of this. So these are the some result, and we got a very good result using this spiral air diverter. So this can create the circulation of the air, and it increases the residence time in the uh, duct. Also, it increase the air mixing. So this design is very helpful to achieve the 100% UV exposure to the air. So this is another time we increases the pitch of the duct. So various simulation has been carried out in the corona in pandemic time. So there is a lot of work we have done, and uh, there is another simulation we have studied the this pitch, how the this pitch if variation is affect the this uh, circulation in the uh, circulation of the air in the ducts, circulation duct. So this is the another air duct is there. So basically, in the previous slides, we have seen we are thoroughly work for the ducting system that in those areas where we have the air central air conditioning, we have the HU, we have the ducting, but uh, those places where we have don't have the uh, air conditioning, so there is no provision of the retrofit of the this UVC light. So we have developed a stand-alone air disinfectant system that is very suitable for those spaces where we have no air conditioning is there. So pandemic SARS-CoV-2 present this UVC radiation that has shown to destroy the outer protein of the coating the SARS corona. That in this way, CVRI, CSIR, CBRI, Roorkee, and CSIO, in collaboration with the CSO, we have developed based on this concept. We have developed standalone air disinfectant system. It can be placed mainly in the closed spaces such as mall, hospital, room, lift. This system is developed to purify the air inside the room space from the various air pollutants as well as the disinfect disinfect the air from the various viruses. Mainly, we have focused mainly on the coronavirus. This apparatus includes a outer frame, coaxial cylinder, and base plate. Then we have a fan to draw the air. So there is a HEPA filter placed in the HEPA filter is placed, and this HEPA filter can help to remove up to the 99% of the indoor pollutants. We have carried out the number of simulations. So the this is the where we have the inlet and recirculating the air in the spiral form. So by recirculate the spiral flow in the UVC chamber, there is a UV light is there, and uh, by using this spiral flow, we are increasing the rotation time. Simultaneously, we are rubbing the air with this wall. There is a special coating is there. So when we rubbing the air with this wall, so it has the added advantage to kill the coronavirus. So in this way, you can see this we are circulating air and rubbing air with this uh, chamber wall. So we have carried out the simulation for this stand-alone air disinfectant solution. The height is 3 feet, outer dia 1.5 feet, inner dia is 0.5 feet. Flow rate we have taken 500 CFM. This very helpful to design the stand-alone air disinfectant systems. So this is a CAD model, basically how we achieve this spiral motion. So we have designed this inlet port. So air is entered into the this chamber in tangentially, and it's come out in the spiral form. There is a number of the HEPA filter is there, and we are entering air from this to this, and it's coming out from this. So in this way, we can see the how we can disinfect the air with using the UVC light, and this system is very helpful. Like in those spaces where we don't have any disinfectant system. So these are the model. This is the model where we develop. So basically, we have carried out the CFD simulation. Is we can see here there is a number of spiral flow is there is improving, increasing the retention time. Also, it is rubbing the this chamber wall, so it increase the uh, chance to kill the virus into the chamber itself. So we have carried out number of the carried out number of the CFD simulation, and we carried out the lighting simulation also using this design. So you can see there is a when we place this light here, so the light intensity is high at this, but this light from the end at the upper end and the lower end, that is sufficient to deactivate the viruses. So this is the prototype we have developed. So this is the you basically this is the unit. We have developed two types of the air standalone disinfectant system. One is the urine unidirectional, that is like this. This is a portable device. It increase the disinfectant and purification efficiency. So we also filed the patent, and we transfer this technology to one of the companies in the pandemic, that is Paras Defense and Space Technology. And later on, we transfer this technology to 8 other companies. So also this standalone air disinfectant system we can use in the different indoors, like a small bed room, medium bedroom, small size bedroom, medium size bedroom, living room, a small kitchen, large kitchen, auditorium hall, a small conference hall, and uh, 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 and we have to there the air changes per hour like this. So that this air changes recommended by the CSIR guidelines. So these are the UVC dosage and retention time we have calculated for the different scenario, like a small bedroom, medium bedroom, living size, small kitchen, large kitchen. So that we have calculated the typical air velocity, what should be the air velocity, what should be the retention time, what should be the UV light intensity in the UVC chamber when the UVE chamber is 1 foot, when the UVC chamber is 1.5 foot, when the UVC chamber length is 2 feet. So in the different scenario, we calculate the retention time, UV light intensity. On the base of this, we can design the chamber. So how should we chamber is there. So these are the basic calculation to calculate the retention time and the UVC dosage required to kill the coronavirus. 99% coronavirus is there. So this the standalone system is very useful in order to achieve the mixing and displace ventilation effect. Without in this there is a this can be used. This can be used in the closed room, but there is some recommendation is there, like standalone system should not be located directly under the ceiling fan. Standalone system should be located such that air is distributed equally in all direction of the room to promote the rapid mixing of purified air with the exhaled air. The return section of the section or inlet section should be convective zone above the head of the occupant. So these are the recommendation with why to use this air disinfectant system. So with this word, I am stopping here. So I would like to acknowledge for this work. So our previous director N. Gopala Krishnan, Ashok Kumar, myself, Nagesh Babu, Chandan, Meena, Kishore Kulkarni, Nishant Kapoor, and this work has been done in collaboration with the CSIU or MTech. So with this word, I am stopping here. If anybody have any question, any queries, so I will be happy to answer you. Hello. Hello.
Thank you, sir, for
Yes, sir. Yes, sir.
now. Question is open for session is open for question answer. Dr. Mulli,
Ye- Yes, sir.
please actually allow me 5 minutes. You manage the session.
Yes, sir. Yes, sir. Uh, any query from audience side?
Sir, I ask you some few.
And I would like to say that this technology, this UVC light ducting system that has been implemented into the CSIR headquarter. Also, we will I will this technology has been implemented in the Parliament House also. So this is one of the best technology that our minister Dr. Jitendra Singh has appreciated to the entire CSI for this technology. And this standalone system has been sold to 8 different companies that has been implemented in the entire country. Yes, you can ask if
Okay, sir. A question is, sir, is this model removes pollutants? It will clear any pollutants like carbon dioxide, sulfur dioxide. Is only killing coronavirus or any other removes the pollutants from
actually,
the.
basically, this system, we can say the if we talk about the standalone air disinfectant system, it is not only the pure air purification. It is doing the purification as well as the disinfect the air also. So in the purification, we are removing the particle from the air. But in the disinfectant system, we are deactivating the virus also. This is the major difference with this standalone air disinfectant system with the existing air purification system.
So here one thought, sir, that this model, this model is fit for indoors, I think,
Ah, yes, yes,
closer indoors. Am I right, sir?
yes.
Sir, but I'm speaking from Hyderabad, but what I observed
Mhm.
in Corona time, patients who are admitted in more sophisticated corporate hospital, the recovery rate is less. The
Uh-huh.
people who are in villages, their
Uh-huh.
recovery rate is high, according to my knowledge.
Hmm.
So finally, what I came to know that the people who are in the indoor,
Hmm.
uh, they,
Hmm.
they, they didn't get a proper oxygen, a clean oxygen,
Hmm.
and
Hmm.
even if they got some oxygen from the synthetic oxygen or something, it causes to other side effects. So
Hmm.
what I finally suggested that indoor air is not good for recovery from the corona. I'm right, sir.
Yes, sir. This that is why we developed this system, na?
But you are saying it's only for, sir, you are saying that it's only fit for indoor only. Indoor, okay, inlet air is coming out. But what is about outgoing air?
But why we actually in the when we have the fresh air, so why we'll use this system, na? Suppose
Okay, sir,
in
you are
the
saying
in
fresh
one
air.
hall, suppose in the one hall, one coronavirus infected person is there. Okay, and we have no air disinfectant system is there. So when this person exhale the air from their mouth, so virus will come and it will infect to the other person. I'm right.
Yes, yes,
So
yes.
in the indoor, like there is a this condition like there. But when we use this standalone air disinfectant system, this continuously recirculate the air from this device. When there any virus is passes through this device, so it get deactivated, and the percentage to get deactivated this device is 99.9 percent is there. So virus going through these devices is automatically get uh, uh, deactivated. This is
It
the
means
basic.
this device is useful for inlet air and outlet air also,
Yes, yes, yes.
both.
It
But
is recirculating there.
the light used is UV light.
UV light, yes.
UV light is which is fit in within the machine.
UV light. Wow, can you repeat? What do you want to
Is
say?
it is the UV light fit in the machine inside the instrument or outside the
Yes.
instrument?
No, inside the UV because UVC light we cannot put in the outdoor condition. It is very harmful
Yeah,
for
yeah.
the human eyes. So it is
That's
in the closed chamber. So
yes,
it is
yes.
in the closed chamber. So radiation do not come outside into the outside in the
Oh, yeah.
room. So
That.
there only passes through the UV light.
Oh,
That is
okay.
exposed air exposed to the UV light only.
So that is my question. You are using UV light, but I thought the UV light may cancer like that.
But it
So,
is in the closed chamber. No light is coming out.
sir, is it find that is there any data available that at what temperature the coronavirus can die, sir? At what temperature can?
Actually, there is a number of paper available that you can see when the temperature is increases. The uh, chances of the coronavirus is reduces. I know.
So what is specific temperature, sir?
Huh?
Specific temperature for the killing of the coronavirus.
No, there is no specific temperature. Till now, no study can say that there is at a particular temperature virus can be deactivated. But that is the recommended temperature is more than 50 degree. है ना? But
Yeah.
in the 50-degree temperature, a human cannot live. That is the one criteria. And similarly, the humidity, that humidity less than 40%, that for desirable for the virus. When we increasing the humidity, the chances of the virus is goes low. But more than 80% of the humidity, the human, this is uncomfortable for the human. So the various agencies is recommended the humidity should be from 40 to 70%.
Okay.
But high temperature, there is a chance that there is no, though no virus is there. At the low humidity, there is a lot of chance that coronavirus could be there. That's COVID.
Is your model marketed, sir? Is this
Yes, it is available in the market, and we
is
are
available?
working on the another prototype, that is the prototype for like tabletop. That is very compact. So it is in the development phase. Of very soon we come with this technology into the market.
Okay. Thank you, sir.
Thank
Thank you for
Thank you, sir, for very much informative and wonderful talk. Really, you have you have taken time and given us 2 days session. And thank you very much, sir. Any more question? Okay. So we are closing this meeting. And kindly wait. I want to make some announcement regarding the test. Kindly wait, all the participants. Thank you, Tabish, sir. Thank you very much,
Thank
sir,
you.
for your kind
Thank you.
cooperation. Thank you, sir. Dr. Murli,
Yes,
please
sir.
stop the recording.
Okay, sir.
I am having one small announcement for